Today I will be like introducing to you what spectral graph theory is. Okay, so the first part is we are talking about adjacency matrix. So, and the other one incidence matrix. What is an incidence matrix? Okay, so I will give you time to grasp. So, it is an n by n matrix such that we write every entry as 0 if I is not adjacent to j. So, this is the notation that I will use for adjacency. Okay. Or we also have seen I comma j does not belong to an edge set, okay, as a tuple. We can also look at it that way. And 1 if I belongs to or I is adjacent to j. So, this is the usual matrix that you know. And what about incidence matrix? It is a n cross E matrix. So, what is the E? Number of edges, right. So, in our usually we are like in standard books, if you see, they follow n to be number of vertices, and if m is number of edges, then we say it is an n cross m matrix, right. So, what is the relation? How do you define the matrix, guys? So, we have Bij as a matrix. So, since I said n cross m, every row represents again vertices. So, vertices we label from 1 to n, and edges suppose we label from 1 to m, E1, E2, Em. Then if there is an edge which is incident on the vertex I, right, an edge Ej, then you write a 1 over there if edge Ej is incident on I, right. So, this is all you know. So, what do you expect like when you hear the word spectral graph theory? What are you going to study? Like you people must be having some hopes and expectations that you will be studying, right? Anything specific, anything that strikes you? But before we go into that, let me just give you a simple comeback for the subject. Okay. So far you have studied almost algorithms, I guess, and you have not had an I mean, you did not dirty your hands with proofs, right. So, what is your take on proofs? So, I will give you one simple interesting fact about proving certain things. Okay. Suppose I give you a graph. In terms of graphs itself we will speak. Suppose I give you a graph, say on n vertices. Okay. I want my graph to be heterogeneous to the core. How much heterogeneous my network can be. So, one immediate thing what would strike you all is like every vertex has a different degree, right. That is one simple heterogeneity that you can see. Every vertex has a different degree. If that means what? Then my graph is, at least I can say it is heterogeneous, right. So, can we have a graph where every vertex has a different degree? So, this is about an introduction. And for spectral graph theory, as you have seen lots of networks you come across, okay. Like communication networks, electrical networks, or social networking is there. Apart from that, physics collaboration networks, which are these are available online, you can see. Suppose I give you such a large network, but you cannot visualize anything as the order scales up to 100,000. Okay, even 10,000 we can't see anything. I guess more than 20 we can't see anything on board also. So, if we are talking about higher order networks, then if I am posing you with a problem, how can I solve those things without looking at a graph, right? I cannot look at a graph and say whether it is connected or not connected, for example, right? Or can I just say that the maximum degree of this network is say 5080 just by looking at a graph on 100,000 nodes? It is not going to be that simple, I guess, right? So, to handle such massive scale, even otherwise also if you see, matrices play a major role, and they are actually called as dual of graphs, okay. Like they both matrix and graphs, they play dual roles. If I know some properties of graphs, I can translate them into matrix language, and similarly any property of matrix I will try to interpret it using my graphs. especially for a 0-1 matrix, for our case say undirected unweighted simple graphs. Okay. The same thing we can extend to directed graphs, weighted graphs, and whatnot. You can just extend, keep on extending the principles that are existing. So in this direction, we'll talk about first graphs. So what do you know about speciality of certain classes of graphs and their adjacency matrices? Have you seen anything special? Anyway, ultimately our goal is to connect the structure of a graph and its matrix properties, especially using the spectral properties. So to begin with, given a matrix or given a class of graphs, have you ever realized that these classes of graphs have a very special matrix representation? Symmetric matrices. It's a 0, 1 matrix, undirect, if we are talking about unweighted, right? Even if it is weighted, then it's going to be symmetric. So that is another property we can see about complete graph. Then what about cycle graphs? Cycle paths, they are all very simple structures, right? Then they should give us very simple matrix. Okay, so we'll go into these parts. Excuse me. Okay, so as you guys said, I'll just write Kn is a complete graph and its adjacency matrix. We'll start with adjacency matrix. In due course, we'll touch upon other types of matrices also. Okay. So this is nothing but a complement of identity matrix, or in mathematical terms, you write it as the matrix of all ones minus the identity matrix, right. So this is also represented as Jn minus In, where Jn is nothing but matrix of all ones of order n by n. And In, you know, its identity matrix. So what about Cn? The cycle on Cn's are nothing but cycle on n vertices, just a cycle. We are talking about adjacency, only adjacency matrix. We'll go into the other classes later. We'll start with adjacency matrix. Come on guys, let us call a cycle. If you want to pictorially represent it, take a 1 and I have 2, 3, 4 and so on. I can just have n and there is going to be an edge connecting 1 and n. Each row will have only one ones. It will be a tridiagonal matrix, is it? So what is a tridiagonal? So you have to also explain that. Above the main diagonal, it's not tridiagonal, right? Tridiagonal means above the main diagonal you have 3 diagonals, okay. But now you will have only, is it that difficult there? By the time you could have even drawn the adjacency matrix and told me what the answer is going to be. Okay, so I think I'll go to the next page to show you. So the matrix, as we know, will have all diagonal zeros, okay, and since I have given you a labeling also, a proper labeling, we can think like consecutive edges are labeled with consecutive integers, then you can immediately see that the vertex 1 is going to be adjacent to 2, 2 is adjacent to 3, 3 is adjacent to 4 and so on. N minus 1 is going to be adjacent to n and n is going to be adjacent to 1, right. So that means what? It will go over here, or since it is a symmetric matrix, again cycle we are talking in terms of undirected graph. So you will also have a similar representation in the symmetry part also, right. So it's not tridiagonal because you will have a 1 hanging out on the top corner, top right corner. So it's not diagonal, it's not, you can just think of this as a very special circulant matrix. We call this as a circulant matrix, where there is a circular movement for every integer. Like if you think of the integers are placed at diagonal 1, then 1 right shift kind of a position you can think of. So actually I could write it even here. So, if I write a 1 here, then it will look circulant instead of this 1 here, okay, but still we have a 1 over here, okay. So, that is the idea, we still have 1 here, and below diagonal, will you have a below diagonal entry here? Symmetric we are talking about, right. So, that confusion is not there, right, okay. So, this is one special class. If we are talking about a path graph, obviously we will not have the one on the extreme right, that no edge is not going to be there, that is the one connected to n edge, that will not be there. So, these are some representation, these classes of matrices actually give you immediately certain properties. So, we will see all those properties and we will go into the spectral properties. So, what do you know about adjacency matrix? What are all the information that you can get if you look at an adjacency matrix? Suppose I give you a matrix which you can observe and you can give me information out of the adjacency matrices. What are all the information that you could give? If it is complete or not, directed or undirected, fine. So, how do you find that? Only this much information you get from a matrix? Here, you should be able to get at least something more. Yes? Degree of a vertex. So, how do you get the degree of a vertex? Row sum gives you degree of the vertex, right. So, that is what I am trying to look at. Some information you should be able to give me, otherwise I do not know where we stand, right. So, by observation we can get all these informations, right. So, further investigations can also reveal a little more detailed ideas. So, now I will shift from here to the spectral properties, okay. So, by spectrum what we mean, how do we compute it? So, we mean ultimately eigenvalues and eigenvectors for a given matrix, right. So, we detour a little bit to linear algebra and let us see what you know about eigenvalues and eigenvectors. Yes, what is an eigenvalue? Say given a matrix, let us talk about a square matrix, we will then go into a rectangular matrix also. So, given a square matrix, n by n matrix, this will be a notation. So, let us also say that it has all entries from real, right, n cross n, just for notation I have given just to mean that it is an n by n matrix and every entry comes from real, right. So, how do we find the eigenvalue for this? Through characteristic polynomial. So, how do we get the characteristic polynomial? So, you are going in for determinant of a minus lambda I, right. So, that is where we are going to talk about eigenvalues. So, given a lambda coming from my complex field, right, it could be complex also, right, and I have set of vectors say x in Rn, this is my notation for a vector, okay. So, we say that lambda is an eigenvalue of A if Ax is equal to lambda x, right. So, what are the things here given and what is existence? If there exists a, right, if there exists a vector, then we will be able to, if we are able to write this Ax is equal to lambda x, then we say that lambda is an eigenvalue and x is the eigenvector corresponding to lambda, right. So, computationally, have you ever tried to compute an eigenvalue? Have you tried this in your school days, college? How do you compute an eigenvalue? Solution of the characteristic polynomial. So, how do you solve a polynomial equation? I am just pulling you out of graph theory, graph algorithms, okay. So, at present there are lots of numerical algorithms where if you are interested you can look into, lot of iterative algorithms are existing for solving eigenvalues, okay. But we will not go into that case, but our idea is we will stick here and we will try to see how much we can connect to, right. So, this equation will give us the characteristic polynomial and we call this equation also as characteristic equation of the matrix A, right. So, what will be the degree of this polynomial? 1, n, Any other answers? Given a matrix of order n by n, what will be the degree of the corresponding characteristic polynomial? I don't see a unanimity here. Is it n, at most n, 1? Anybody else with any other answers? Okay, it is n. Okay, so let us fix on that part. So sometimes we write this notation for a characteristic polynomial, phi g for the graph, okay, and with this is not a, this is lambda. Phi g of lambda or phi a of lambda, depending on the matrix which we are taking, we will also write it as the graph or the matrix that we are talking about. Say suppose I just give you a representation and we will talk about it in terms of this. So this is the characteristic polynomial, and solution of this equation is going to be the root of this equation, if I take this, the polynomial equating it to 0, roots of this will be the eigenvalues, right. So this much we are all clear about at this point of time. And is it always necessary that lambdas will be distinct? And first of all, how many lambdas will be there? Solutions, how many solutions are possible for an n degree polynomial? N, right. So we are in complex field. If it is in real field, your answer is wrong. Okay. In the complex field, for a real polynomial, we can have n roots. So will it be distinct? Next question. Depends on the polynomial, right? Need not be. So these are some basic points that we should be clear. So usually, let me fix the notation again. We'll determine, represent all the eigenvalues in decreasing order, lambda 1 greater than or equal to lambda 2 and so on up to lambda n. So I've given greater than or equal to just to make sure that it could be distinct or repetitive also, but we include everything in here. So there are n eigenvalues possible. Okay. Okay, so with this, how can we now connect to our graphs? I will go as and when we require, we will touch upon other linear algebra properties. I will not bore you at one time with all properties that I want. Okay. So given a graph, say he is more interested in complete graph, what can we say about the eigenvalues for a complete graph? So to see that, we need to do a little bit of computation, but there are certain tricks that we will try to see. So as we have seen already, our complete graph is going to be j minus I, right, it is just j minus I that we have. So if we want to find the polynomial for this, what will it be? Okay, so before j minus I, let us think about Jn, matrix of all ones, right. What is the rank of this matrix? What is rank first of all? So, number of non-zero rows. Is it just non-zero rows? In the echelon form of the matrix, number of non-zero rows in the echelon form, right? But we are given Jn, so what will be the echelon form for it? Except the first row, everything else is going to be 0, right? So what is the rank of this matrix? 1, right. So all ones matrix is going to have rank is going to be 1. Okay. So now what does this tell you about eigenvalues? If you people have had a little bit of here and there feeling, you can immediately guess what will be the eigenvalues for this. So there is only one non-zero eigenvalues for this matrix and everything else is going to be 0. So there are n minus 1 eigenvalues which are going to be 0, and there is only one eigenvalue which is non-zero. So what is that one non-zero eigenvalue? 1. No. N. So it should be either only 1 or n, is it? Not in between. What about n minus 1? There are n minus 1 zeros. What is that one non-zero eigenvalue? It has taken value 1 and 1 said n. So any other choice? 2 to n minus 1. So everybody are convinced that it cannot go beyond n. Is that true? What about n plus 1? 2n, 3n. Okay, you keep pondering over it. I'll get back to this characteristic polynomials. Okay, what does your characteristic polynomial reveal? How do you connect your matrix and the characteristic polynomial and its determinants? So we need to do all these exercise a little bit. If you are bit faster with me, I will also go faster. Sum of the eigenvalues is equal to trace of the matrix. So what is trace? Trace of a matrix A is going to be nothing but equal to sum of all the diagonal elements, right? So A11 plus A22 plus A33 and so on plus ANN, right? And it is also true that trace of A is, in some books you can see they follow this notation, TR of A. Okay. Trace of A is also equal to sum of the eigenvalues, right? So now connecting this with your polynomial, how do you connect this? So every polynomial, what does the coefficients of the polynomial tell you? Given any determinant when you expand it, what does the coefficients reveal to you? So how do you write the polynomial? You should just go back to that. That is a solution of the characteristic equations, right? That gives the zeros of the polynomial, right? So every coefficient, it has a very interesting property that we connect with the eigenvalues, and that is what we will do with the graphs also, right? So if you look at the coefficients of the polynomial, they take a very special property. What is that? Where have I written? Here. So I can write this polynomial phi lambda, right, as if I try to write it as in factor form, say there are n eigenvalues, we have already seen that part, right? So if suppose I write it as say lambda minus lambda 1, lambda minus lambda 2 and so on, product of all these factors, right? This is a possibility, right? Once you know these are the roots, then you can write them as factors in this form, right? So from here, if you see the coefficients of each of the lambda powers of the lambda, what does that give you? Lambda power n, suppose I look at lambda power n, what is the coefficient of lambda power n? In this case it is 1, it is a minimal polynomial already, so we know it is 1. So what about lambda power n minus 1? So there is a very specific format. So if you are talking about coefficient of a polynomial of degree n minus 1 in this fashion, it is going to be nothing but sum of all the lambda i's, right, with a negative sign you will get. So actually the factors would go like this. So you have lambda power n minus of lambda 1 plus lambda 2 plus lambda n into lambda power n minus 1 plus product of 2 elements. All 2 elements you take and take the sum of all 2 element possibilities, right? Every possible 2 element pairs you just pull out and you can write it, right? So it would be something like sigma lambda I lambda j, and I not equal to j. Do I need I not equal to j? Yes, and so on, right? So in this fashion, if we continue, we will end up with our last constant term being the product of all the eigenvalues that we have here, right? So here we are going kind of in a reverse direction, assuming lambda 1 to lambda n are the eigenvalues, we have tried to break the polynomial here. So we can also see that this product lambda 1 to lambda n, what we have here, right? So what is that? It also represents something specific. Given a matrix, it's if you are talking about the characteristic polynomial, the constant term in the characteristic polynomial represents determinant of the matrix, right? So determinant of A is nothing but lambda 1 to lambda n, product of all the eigenvalues. So the trace of a matrix gives you sum of all the eigenvalues, while the product of the eigenvalues gives the determinant of the matrix. right. So, these are some simple things I just want to refresh out of you. Next we will go into minors. What do we know about minor of a matrix? Or okay, let us start with submatrix. What is a submatrix? Have you heard of these terms? Tell me yes or no, so I will give you proper definition. Okay, so we'll because I want to connect the minors with these terminologies whatever we are talking about here. Okay, so I'll just go into that and we'll revert back to what we are doing.